Hi everyone, I am Luinaud, a PhD student at Polytechnique Montréal in Canada. Today I'm here to present you my paper Design Principles for Packet Deparsers on FPGAs. In this paper, we propose an architecture which is generated from P4, a network programming language, and which consumes up to 10 times less resources compared to previous work. So, why do we need packet deparsers on FPGAs? Well, today's data centers are growing in interest. As a result, they have to implement new network protocol. They have to support a variety of applications such as databases, deep learning, and so on. Also, new network links are coming. 400 gigabits per second links are on the way. As a result, data centers need to have network devices that are programmable. Those devices must be flexible, processing platform also, and they must be high-performance platform. As a result, there is a growing interest for FPGAs. The question was, how can we model packet processing on FPGAs? Well, this question is answered. We can model them by following this process. We have a parser which extracts each header of a packet. The remaining of the packet is a payload. Each header is inserted into the PHV packet header vector. Then the PHV is sent to the processing block. The processing block will, according to a code, modify the PHV. Finally, this PHV is sent to the deparser with the payload. The deparser will reassemble the header with the payload, meaning that it will insert all headers and then insert the payload to generate the new packet. It has been demonstrated that parser and processing blocks are well implemented on FPGAs according to the FPGA capacity. However, the deparser should be really more efficient on FPGA. Today, it consumes a lot of resources. So, how a deparser is modeled? Well, the way the deparser works is that you have to indicate in which order each header should be emitted. Here, I present a P4 code that represents a deparser for 3 protocols: Ethernet, IPv4, and TCP. On the right, you have the resulting state machine that can be generated from this code. Since it's just the order in which header should be emitted, it doesn't mean that each header must be emitted. It just says that if a header exists, then it should be emitted before the other one. So, as example, if there is an Ethernet header, then phv.eth should be emitted. And then if IPv4 header is present, IPv4 header should be emitted, etc., etc. So, what is our proposed architecture? Well, our architecture tries to leverage the FPGA configurability capacity, meaning that when you change your program, you reprogram the FPGA. So, this architecture is based on the idea that we should assign to each output bit of the packet a different state machine and a block that will determine which bit should be assigned to an output bit. With this method, we are able to leverage FPGA interconnections that are present on the FPGAs. As a result, we have one block per output bits. So this architecture is duplicated for each output bits in the packet out bus. By doing so, we are able to pre-compute possible transition. So we can implement multiplexers for the PHV bus and the payload, which indicates which bits of those two buses should be connected to each packet out bits. This allows us to significantly improve resource consumption. As example, when we implemented 2 tests that implement Ethernet, IPv4, IPv6, TCP, UDP, MPLS, and VLAN headers, we were able to divide by 10 the amount of resource consumed compared to Xilinx SDNet solutions, while keeping a throughput close to them. Also, we were able to divide by 5 the resource consumption compared to Benasec, while having more throughput. Thank you for your attention. If you have any question, I will be pleased to answer them. In the paper, there is a link that will lead you to the code we wrote to generate this deparser. Thank you.